Now, I'd like to turn to a discussion of the trophic molecules and consider the nature by which these molecules provide nourishment that promotes the growth and survival of neurons and their processes. And I'd like to take you through a really classic experiment in neuroembryology done in the first half of the 20th century by two real heroes of mine, Victor Hamburger, who did most of his work at Washington University in St. Louis, where I did my own graduate studies. I had a chance to meet Victor Hamburger towards the latter years of his life, and it was a real joy to do so. Victor Hamburger is a role model for so many reasons. He was a wonderful scientist, but he had a particular perspective on collegiality, which has certainly enriched his legacy for those of us that know something about him. Victor Hamburger began to be aware of a Italian scientist, a young woman who was working under extraordinary conditions. Her name was Rita Levi-Montalcini, and Hamburger and Levi-Montalcini, a world apart, were doing very similar experiments and not always coming up with agreeable findings. And rather than developing a sort of a competitive adversarial relationship, Hamburger invited Levi-Montalcini to join him in his group in St. Louis, which she did after working through tremendous hardship in the time of World War II. Well, eventually Levi-Montalcini and Hamburger, together with Stanley Cohen, collaborated in a landmark series of experiments that led to the discovery of neurotrophins and a deeper understanding of how they impact the development of the nervous system. Well, here's some simple experiments that they performed. It involves a study of the development of motor neurons in the spinal cord relative to the muscles that they innervate. Now, as I mentioned in our last tutorial, many more neurons are typically produced in each region of the nervous system than actually survive, and that's true here in the spinal cord. What we see in the ventral horn in this illustration in red are those neurons that actually go on to survive the course of development. In green is a population of neurons that are initially produced but die off through a process of programmed cell death. So why should this be? This was a question that Hamburger wanted to explore. And what was the experiment here was to take a chick embryo and delete one of the limb buds, which would have obviously a dramatic impact on the amount of target tissue that would be available for the outgrowth and connectivity of the alpha motor neurons on that side of the appropriate enlargement of the spinal cord. So the result of this unilateral limb blood ablation is that on the ipsilateral side of the spinal cord, there's a dramatic reduction in the population of motor neurons, whereas on the intact side of the spinal cord, the normal complement of motor neurons survives the process of development. So this suggests that there's something about the presence of target tissue that's essential for the survival of the neurons that normally would come to innervate that tissue. Well, in the chick embryo, it's possible to do the complementary experiment. So what Hamburger and his colleagues did was they took a limb bud from one embryo and transplanted it to another, essentially doubling the complement of target tissue that would be available for the innervation of motor neurons from the appropriate segments of the spinal cord. And then after about a week of growth, what was discovered is that on the side of the embryo that has the extra limb bud, there are roughly twice as many neurons that would normally be present. And the control side is the index that allows a conclusion regarding the impact on cell survival from the presence of that extra limb bud. Now, one might have imagined that these extra neurons were somehow induced through mitotic activity here in the ventral horn following this addition of this extra limb bud, but through a variety of experiments we know that that's not the case. The extra neurons that are present here reflect the survival of neurons that otherwise would have died through programmed cell death. So this suggests that there's some factor that's present and released by target tissue that is essential for the survival of neurons, and that such factors might be important in establishing the appropriate complement of neurons that connect to target tissues. So these experiments allow for two principal conclusions. That there is decreased programmed cell death of a motor neuronal pool with augmentation of target tissue, that is, with the presence of an extra limb bud. But it also illustrates that with reduction of target tissue, there's an enhancement of programmed cell death, leading to a depletion of those neurons that otherwise would have survived. So this suggests that target tissues release some kind of a substance. We now call that substance a trophic factor that is essential for the survival of neurons. And this substance might actually be quite critical for establishing the appropriate complement of neurons that innervate a target tissue. Now, we think that through a variety of other experimental evidences, we believe that trophic molecules also operate at the level of individual axonal branches, not just the survival of the entire neuron. And this becomes critical for establishing the appropriate patterns of convergence and divergence as neurons innervate their target tissues, be they targets in the periphery or targets within the central nervous system. So here's two examples from the peripheral nervous system. In early development, alpha motor neurons innervate individual muscle fibers, and it's possible to find multiple collaterals from different alpha motor neurons supplying the very same muscle fibers. So here in this illustration, for example, a single alpha motor neuron might send branches that innervate each of three individual muscle fibers. In autonomic ganglia, we may see something quite similar. There may be collateral branches from a single preganglionic neuron that innervates multiple postganglionic neurons. Now, this is quite intriguing because we know that in the mature nervous system, a single muscle fiber is supplied by a collateral from just one alpha motor neuron. And likewise, a ganglionic neuron that lacks dendrites, such as what we have illustrated here, receives its synaptic inputs from a single preganglionic neuron. So there's some kind of sorting process that must play out here to establish this appropriate degree of convergence and divergence. And a key mediator of this competition seems to be neurotrophins. Well, a variety of studies done in these systems and others have given rise to a set of propositions that we sometimes call the neurotrophin hypothesis. So the neurotrophin hypothesis goes as follows. We imagine that in development, the survival of neurons and their axonal connections depends upon the availability of a trophic factor that's present in some minimal quantity. Such trophic factors are synthesized and released by target tissues. And again, we think that they're present only in very limited quantities. And this sets up a competitive scenario where the survival of neurons and their specific connections depends upon successful competition for the acquisition of that trophic substance that's present only in limited supply. And in this way, we imagine that for that single muscle fiber, only one axon can acquire sufficient trophic substance to promote the survival of that connection. Similarly, for a ganglionic neuron, so that only one preganglionic neuron can acquire sufficient trophic support in order to maintain the viability of that connection. Now, let me just back up for a moment and highlight interesting and accurate feature of this illustration. Notice that there are fewer connections in these immature neurons compared to the more mature form. So the overall numbers of synapses is increasing even as competition is playing out in the numbers of inputs that is the number of individual axon fibers or axon collaterals that come to innervate a given postsynaptic cell, is decreasing. So there is a winnowing down of the numbers of neurons that are interconnected, even while there is a net increase in the numbers of synapses that are being formed on these postsynaptic targets. So in this autonomic ganglion, there may be a winner-take-all outcome here, such that all of the postsynaptic targets that are available on this ganglionic neuron are now occupied by synapses that are elaborated by a single preganglionic axon. Okay, let's get back to our neurotrophin hypothesis. So we've emphasized that in brain development, this is going to be really critical for mediating competitive interactions among different axons that may be competing for the same postsynaptic targets. We'll see some examples of that in the developing visual system in our next tutorial. But I'd like to just make a point, and that is that in the mature nervous system, neurotrophins remain very important molecules in shaping the structure of circuits in the central nervous system. And this is especially true in the context of plasticity following injury. One phenomenon that we'll explore later in this unit is that as nervous tissue is recovering from injury, many of the mechanisms that were important in establishing connections in brain development become reactivated. So many of the genes begin to express the substances that were important in building connections in the first place as a means for promoting regeneration and regrowth of connections within the central nervous system. Now, this process is modulated in various ways. We'll eventually come to that. But for now, I want to emphasize that neurotrophins remain important in shaping the structure of connections even in the mature brain. And this is especially important in considering how the brain responds to injury and disease. But it's also important in understanding how sensory motor experience can shape connections within the brain and thereby instill learning. So, for example, when we acquire a new motor skill, when we practice a sport or a musical instrument or a new dance step, we imagine that there is some kind of plasticity that's taking place. And neurotrophins very well may play an important role in mediating the competitive interactions that we hope will eventually build a more efficient circuit that will reinforce those patterns of connections that instantiate the acquired skill.